let me quickly make a few introductory remarks to welcome Vicki Kaspi, who's going to give our colloquium today. Now, we were very fortunate. She gave us a lovely Bunyan lecture yesterday evening, introducing us to the topic which you will hear more about today. Yesterday evening was a public lecture, and I think it got the students and the public very enthused about the interesting discoveries. But you will hear a little more detail and a little more science about them in today's lecture. Now, a few words about Vicki. She started her academic career at McGill, and then went on to graduate school at Princeton, where I actually first met her when I was at the Institute. And after that, she spent a little time at, a sojourn down under in Australia, which we won't count, but a little time at Caltech, and then back to MIT as an assistant professor before returning back to her alma mater to McGill, where she's the Trottier professor of astrophysics, and has developed a really dynamic group, as I mentioned last night. A lot of really good students, really exciting work, which you're going to hear about some today. Of course, Vicki has numerous awards, like last week's speaker. She is a member of fellow of the Royal Societies, in this case, the Royal Societies of Canada as well as Britain. She, of course, has numerous awards, and given that she's in Montreal, it's probably appropriate that in her awards list there's a certain number of prix as well as prizes. But I think most notable, I guess, the Rutherford Medal. That's very appropriate for somebody from McGill. After all, he did a lot of his great work there. And most recently, the Shaw Prize for astrophysics, which is a very nice honor. But she's going to tell us today about some new work going beyond the stuff that was given all these awards. And I think it's very exciting to hear about the progress in this new field of fast radio bursts. So, Vicki, take it away.
Hey. So thank you very much. I guess for some of you, this is, like for me, a little bit of deja vu from last night. I don't know how many of you, just a show of hands, how many of you were there last year? Oh, you were there, and you came back, that's so sweet. Okay, well, I'm going to be telling you about fast radio bursts, which is a branch of, I wouldn't say totally new, but very much in fashion areas. Astrophysics in the time domain, so talking about varying, things that are bursting. Here's an example, just to set the mystery in motion. Here's some data now. This is a fast radio burst. It's one studied by this then undergraduate Jacob Faber in a paper. You read all about this burst in a paper. These are events in the radio band, as I'm going to explain, cosmological distances arriving at Earth with truly remarkable morphologies and phenomenology. Basically, as I'll explain, we don't know what they are. It's a mystery. But I wanted to open with some just really spectacular data. But notice you can already see the basic properties of these objects that I want to convey. These are bursts of radio waves that last just a few milliseconds. Just a few milliseconds there, and it's gone. You can see the interesting spectral behavior, in this case in the band from 400 to 800 megahertz, obtained using, and I'm going to describe in much more detail, the CHIME radio telescope in Canada. And here you just see all sorts of spectacular features, in some cases on microsecond scales. Here's another one, just eye candy to open the talk a little, at least to me. I could stare at these for hours and what is that? The horizontal bands in this case are bad radio frequencies where there's terrestrial interference, cell phones or something. But the bottom line is, as I said, fascinating phenomenology. These events newly discovered only in 2007. And as I'll explain, we know now they're coming from cosmological distances, but we don't know what they are. They are an astrophysical mystery. And I wanted to put them a little bit into a broader context of radio astrophysical transients. This is a lovely plot made by our team postdoc. She's based at MIT, Kenzie Nemo. On the x-axis is a measure, one way of measuring time, so millisecond duration objects in the radio band are in this region, microsecond, nanosecond. On the y-axis is a measure of luminosity. It's like luminosity density. Here, in astronomer kind of units, ergs per second per hertz, but basically this is how bright radio transients can get. And the sorts of radio transients in the sky that we have observed for many, many years are in this region of the diagram. For example, radio pulsars. These are highly magnetized neutron stars that are Nobel-celebrated objects. They sit in this part of the diagram, typically millisecond, but some microsecond type behavior also, and at these luminosities, these intrinsic brightnesses. There's one very famous radio pulsar in the Crab Nebula, the remnant of the supernova observed by the Chinese in 1054 AD. The Crab Nebulas contains a radio pulsar that has giant radio pulses. Those are some of the brightest single radio pulses that had been seen from our galaxy until fairly recently. The Crab actually occasionally has nanosecond type bursts, but never mind those. The fast radio bursts that I'm talking about sit way, way up here, many, many orders of magnitude more luminous than anything we've seen in the galaxy. So the total, and this is, I said they're at cosmological distances, they're very far away and they pack quite a punch. So that we're talking about something energetically that's really qualitatively different. And this is just a slightly different version of this plot that generalizes to longer timescales than just milliseconds. There's a whole phenomenology of radio transients, the astrophysics and the time domain that I won't tell you about, but astronomers know and love magnetic cataclysmic variables. Those are white dwarf stars and all sorts of things that. But the FRBs are at the level of quasars, at the level of supermassive black hole type energetics. And yet last just a few milliseconds. So we don't, in terms of luminosity, they're very bright. So I'm just trying to, whet your appetites. So just again, they're coming from cosmological distances, which is inferred, and at least initially, from their dispersion measures, which I'll explain. Probably they're very bright. And they're not like a strange anomaly that's very rare. These are ubiquitous. The all-sky rate, roughly speaking, if you could observe the entire sky all the time, it's very hard to telescopes to do that, but if you could look at the entire sky all the time, you'd see about 1,000 of these per day. So it's something common in the universe. So common. And their origin's unknown. So this is the first FRB that was ever detected, and here, in the previous plots that I showed you, they looked vertical as if all radio frequencies arrived at the exact same time. In fact, that's not how we observe them at all. The standard way of, the raw data, when you take it from the radio telescope, digitize it, this is half a second of data on the x-axis, and this is radio frequency on the y-axis. The high radio frequencies arrive before the low radio frequencies, and that's dispersion of radio waves by cold plasma in either the interstellar or the intergalactic medium. We're very familiar with that phenomenon from galactic radio pulsars, like the Crab pulsar and others. We see that throughout the galaxy, this kind of radio dispersion. It's just cold plasma dispersion that we see in E&M. And in fact, if your eye is good, you see this is a frequency squared law. So the time delay between any two radio frequencies, it goes as 1 over frequency squared, with the constant of proportionality, this dispersion measure, which is basically the integrated electron density along the line of sight. So the more plasma there is between us and the source, the greater the dispersion. So an object that's really, really close will look more vertical on this plot. And I should say that the de-dispersed pulse, once you correct for this amount of dispersion, and you correct in software for it, the de-dispersed pulse looks like the inset, where there's just basically radio noise. Now we're summing over all the radio frequency channels. Noise, the pulse that lasts a few milliseconds, and then nothing, just back to noise. And this particular burst that was seen at the Parkes radio telescope, that's a radio telescope in Australia, 64-meter aperture. It has a 3-story building underneath it. This one appeared and was never seen again. They saw the first one kept watching and never saw it again. And they kept watching for a long time because they knew from looking at this it had to be from a cosmological distance. And the reason they knew is the degree of dispersion was enormous. So we actually know the distribution of plasma in the Milky Way. This is a map, contour plot of the distribution, basically of dispersion measure of the integrated electron density. If this is the galactic center, and this is where the solar system is. And these are, spiral arms. This is a contour plot showing lines of constant integrated electron density, constant dispersion measure. This is just a 2-dimensional slice through a 3-dimensional model. So in any direction, if we detect some source in the galaxy, we know the distance just from having measured that dispersion measure. This is very well calibrated, for the most part, by galactic radio pulsars. So we've been studying radio pulsars, these highly magnetized neutron stars, for years, and many of them have independent distance estimates. So this map has been quite well calibrated, so pretty reliable. And in particular, what we have from the map is that in any direction, we also know the maximum dispersion measure that the galaxy can contribute. So at some point, the galaxy runs out of free electrons. And so in any direction, you measure a certain dispersion measure, you could tell if the object's inside or outside the galaxy. And so that's how we call it Lorimer burst after the Parkes astronomers who were observing it, or at least the lead author, Duncan Lorimer. They knew the second they saw this burst, there was something shocking about it, because the degree of dispersion in our arcane units, it was 375, that's of this source, of this Lorimer burst, whereas the maximum from our known, well-calibrated plasma maps of the galaxy was only 25. Not just a little bit outside the galaxy, way outside the galaxy, and the distance had to be cosmological because we know that the amount of plasma in the intergalactic medium is very, very low compared to what's in the galaxy. So immediately, this is why they kept observing it and kept hoping to see it again, and they never did. But it was quite shocking, and naively it implies a cosmological distance, as I said. And therefore, a tremendous luminosity. Okay, but let's talk about just, again, how cosmological is cosmological. Roughly speaking, from models of the IGM, which, spoiler alert, we can now check. But before FRBs, we couldn't. So before FRBs, from IGM models, we knew that the dispersion measure should be roughly 1,000 times the redshift of the galaxy, redshift from the Hubble expansion. And so if you plug in the dispersion measure of the Lorimer burst, that gives you a redshift of about 0.3, which is quite large. That is cosmological distance. And it corresponds to about a billion parsecs, a gigaparsec, which is quite far, a significant fraction of the size of the universe. But they also knew that this had to be an upper limit to the distance. It wasn't guaranteed to be at a cosmological distance from the dispersion measure alone, because all you measure is that integral. You only get the integrated electron density, and that has multiple contributions. From the path of the source all the way to Earth, there's multiple places where you can have dispersion. So there's the Milky Way interstellar medium itself, which we know and is really well mapped and calibrated. We believe the Milky Way has a halo, much more tenuous halo around it, and we think all galaxies do. But we don't exactly know what the density of that halo is. There's the intergalactic medium contribution through the cosmic web as the source passes, that gigaparsec distance. And then presumably it comes from some galaxy. Presumably the source of this weird object is in a galaxy that has its own interstellar medium and contributes some dispersion measure right there. And so, we don't know where how it's all distributed. So let's say you just hedge your bets and you say, okay, let's say it's halfway there. And you put half of the dispersion measure in the Milky Way halo and an IGM and half in the host to be conservative. It still gives you a 500 megaparsecs. And so that's still pretty far. And it gives you the energy scale, if you make that assumption. And now you could say, well, what if it's a really weird galaxy and there's tons of electrons there and it's actually really close? Well, okay, we couldn't rule that out. So it just seemed unlikely. And so this is sort of your cartoon picture, which I'm going to come back to, that there's multiple sources of the dispersion measure. So you might say, well, why don't you just look and see what kind of galaxy is there? Why don't you just check and see, is it a big honking spiral galaxy with lots of stuff in it, which would say that there's a lot of dispersion. It's not at a cosmological distance. But the problem is that radio telescopes have very poor angular resolution, diffraction limited with many centimeter wavelengths. So the 64 meter Parkes dish is probably something like the size of the full moon is the angular resolution of the telescope. There's 1,000 galaxies in that kind of region. You'd love to know which galaxy because that would tell you the redshift, it would tell you the exact energy scale, and then you could see even what kind of galaxy is it? Is it a young galaxy that forms stars? Is this a young object? Or is this, colliding neutron stars, like LIGO sees, which would tend to be old objects because you have to, make the neutron stars and let them produce have gravitational. Those are old sources. So what kind of galaxy? You'd love to know this, but we just couldn't do it given the angular resolution of the Parkes telescope. And even if you went to a much larger telescope, it's lambda over D. If you went to increase D and go to, say, at the time, the biggest radio telescope was the Arecibo telescope in Puerto Rico, biggest radio telescope. It still it's not good enough. What you really need is an interferometer. You need a telescope with tremendous long baselines. So the very large array is what you would like. And so you say, well, why don't you just go to an interferometer and look? And the problem is that this is a transient phenomenon. You don't know when or where to look. And it has a tiny field of view. The chance of just catching an FRB with a very large array or a large interferometer is very small. So that's what we knew for a while. That's where we were at for some time. For a while Parkes was operating, there were many more theories published about what these were than there were FRBs known. That was kind of a weird situation to be in. The source has a very compact size. If it's on the order of a millisecond, then you're talking, at most a few hundred kilometers. So it smells like a compact object, neutron star, something, perhaps a black hole. The energy, though, I've tried to say, it's incredibly powerful. The truth is it's not hugely constraining because, for example, gamma ray bursts are much more energetic. Those are gamma rays. These are just radio waves. Gamma ray bursts can have isotropic energies, 10 to the 53 ergs, way bigger than what we do. And by the way, you might be wondering, well, maybe the phenomena are related. I have a graduate student who's looked into this, and I know I was talking at lunch. Thank you, with the grad students, and you were looking at to see if our FRBs are coincident with Fermi FRBs, and we were doing the opposite, looking So anyway, we haven't seen any coincidences. Don't stop looking because you never know. Don't stop. Don't stop believing. The radiation mechanism must be something coherent. If you just interpret the radioluminosities, given the compact size as a brightness temperature, it's ridiculous. And I know Roger Blanford gave a talk last week where he also mentioned this. But you say crazy, but it's radio pulsars in the galaxy have shown that not at this scale, but certainly also this non-thermal. Radiation almost certainly must involve a large magnetic field. You might say, well, okay, it has to be some cataclysmic event, maybe a supernova. But the problem is that the opacities in supernovae are quite high. You don't expect the radio waves to easily escape. So that's one problem. And then you might say, what about like a neutron star merger, these sources? Well, the truth is we say 1,000 per sky per day. That's way higher than the GRB rate, the inferred rate. But really, the argument against the cataclysmic models is not what I just said. It's that it turns out, even though the Parkes team looked at that Lorimer burst over and over again, never saw another burst from it, some of them, we now know, do repeat. So that's a huge clue. And by the way, there's a theory wiki, because there's always new theories, and I encourage you to have a look at that. One of the favorite models, and I'll come back to this one, is magnetars. That these magnetars are ultra highly magnetized young neutron stars that we know of. We know of a couple dozen in the galaxy. In fact, if you want to see the magnetar catalog, we maintain it at, well, it's maintained at McGill University by my group. It's a little out of date right now, but never mind. These are highly magnetized young neutron stars that we have observed to have huge X-ray bursts. X-ray telescopes often catch these, the Fermi GBM gamma ray burst monitor will sometimes see these X-ray bursts from neutron stars where the magnetic fields are extremely high, higher than 10 to the 14 Gauss. That's a couple orders of magnitude higher than conventional radio pulsars like the Crab pulsar, which is around 10 to the 12 Gauss. So these are much more highly magnetized neutron stars. And they have huge magnetic reservoirs, so 10 to the 47, 10 to 49 ergs. And we know, we don't exactly know the mechanisms, but observationally it's very clear that the magnetic fields somehow render the star unstable, either some sort of crust cracking or magnetic reconnection. There's lots of theories about this. It's a very interesting area of research. But they're not known for, so they've had extremely powerful X-ray and gamma ray bursts, but they haven't been known for ultraluminous radio bursts. But still, it's an object that has enough energy to account for the energy budget of fast radio bursts, and it's compact, certainly high magnetic field, non-thermal radiation. Yes, this is a good candidate, and we'll come back to that. But it's certainly a good candidate if these things are going to repeat. And the first one that we found to repeat was the first one that was seen not at the Parkes Observatory. And as I related last night, there were a lot of surprises at Parkes where at first they thought they might just be terrestrial interference of different types. But then they figured out that they're not. Some of them were, but you heard of, if you were here last night, you heard about the microwave oven story, so I won't repeat it. But they were certainly very delighted when it was my team that found the first FRB at a telescope other than Parkes. We were using the Arecibo telescope, 300-meter aperture in Puerto Rico. There you can see it. And we found one FRB, and we were really thrilled, and we kept staring at it because we knew that Arecibo was very, very sensitive. So if we were ever going to detect repetition, this was the instrument to use. And it took a long time. It took months of staring at nothing, getting kind of boring. But then one day, we detected, whatever it's a dozen bursts in the span of about an hour. And so this was the first repeating FRB, here shown de-dispersed. These are the different bursts that are de-dispersed. And immediately, so much in one observation. And it's so wonderful. As a grad student then, Paul Schultz, who did this observation so quietly and then came to us with, our jaws dropped. And we didn't know they repeated. But it immediately ruled out cataclysmic models for this source. It also, just the phenomenology was shocking. I mean, if you look, some of the bursts were incredibly bright. Look how bright this one is. Some are really faint. The spectra were different. Some are really bright at the bottom of the frequency band. Some are really bright at the top of the frequency band. Also, just from the fact that we hadn't seen it for months, and then suddenly in an hour we saw 10, we knew it's highly non-Poissonian. This is not a random bursting thing. There's something going on. It's non-Poissonian. And all of that was interesting phenomenology that teaches us something about the burst engine. But never mind all that, it also gives you an opportunity to do sky localization. Suddenly you know where to look, and if you're patient enough with an interferometer, and so we had to convince the directors of the Very Large Array to observe, and we kept observing, and of course the source didn't cooperate at first, and we had to keep begging for time, and they were very kind, and eventually, so after 50 hours of observations with no burst, which is a long time on the Very Large Array, then finally we, in one test observation actually, the source was bursting. And boy were we glad, and here's the burst. It immediately localized it to a region on the sky that was just tiny, an square arc second, with the same dispersion measure as we'd been seeing at Arecibo in the repeat burst. So we knew exactly where it was, and we knew it was the same source, had the same dispersion measure. And then once we had that position on the sky, we can then go to an optical telescope, beg for time there. It wasn't hard. They all wanted to give us the time. We went to the Gemini telescope, and to our amazement at the location specified by the VLA, we found a galaxy. And at a cosmological distance, too. We can measure the redshift of the galaxy, exactly as the dispersion measures. If you didn't believe the dispersion measure story before, well, we have a confirmation. But curiously, it was this puny little tiny dwarf galaxy that, and I don't mean to denigrate, because today I was also talking to another grad student, where are you? Maybe he didn't come, but who's working on dwarf galaxies, trying to do a survey. There you are, yeah. No, so I don't mean to denigrate that. They're wonderful, but we were shocked. We were just shocked that it was in a dwarf galaxy. Like, why? But at least it confirmed the cosmological distance. And I should just say that the answer to the question of why isn't it a dwarf galaxy, it turns out it was a red herring. So although we were very surprised by it to start with, meanwhile, another telescope down under called the Australia Square Kilometre Array Pathfinder ASCAP telescope, it is capable of detecting FRBs as well and localizing them at the same time. It's the detection rate, they get about a dozen per year, maybe, I think that might have increased recently. And they started seeing other fast radio burst sources. So here, the white circles denote their localization regions. And you can see these are optical images of different types of galaxies. You see there's one beautiful one in the spiral arm of a galaxy. All of these are now larger galaxies. This one seems to be on the outskirts of a galaxy. All of these are larger galaxies, and none of them is a dwarf galaxy. In fact, there's now been a few dozen localizations of FRBs to galaxies, and only one other one is in a dwarf galaxy. So that's sort of interesting. And this is so important to get these redshifts. Once you have, in other words, to see what galaxy it's in, because then you measure the redshift. You know the distance. And you can then, if you have your assumptions for the Milky Way halo and for the interstellar medium, and you know the distances, then, and you see what kind of galaxy is, you have an estimate for the host EM, you can then start to learn and measure the IGM component. And so here is a beautiful, spectacular plot by the ASCAP team where redshift of the FRB, that's the redshift of the host galaxy, is on the x-axis, and the dispersion measure excess, that is after taking the observed dispersion measure, subtracting off the galactic, I should have put Milky Way, the galactic component, the halo of our galaxy, and then a host contribution that you can now estimate a little bit better. Not perfectly, but you can estimate it better. And you see they had just a few localizations, and this black line is not a fit to the data. It's the prediction from Planck cosmology for given the matter density that we think is in the universe and the fact that it should all be ionized. This is the famous missing baryon problem, where we believe that there's, in the intergalactic medium, there's baryons, of course, they should all be ionized, but we can now see it. This is the prediction. The gray region is kind of an uncertainty region due to the fact that there's different lines of sight. There's a cosmic web. There's variation. For any redshift, there'll be some range of dispersion measure. But this was just a spectacular confirmation. We call it now, in the community, we call it the Marquardt relation. This DM redshift relation that identifies the missing baryons in the universe. It's called Marquardt relation after J.P. Marquardt, who was the lead author of this paper, who also tragically passed away not long after the paper was published at a very young age. And so as a community, we now call this the Marquardt relation. Yeah, so what I'm trying to say is that, I've been sort of, and, we don't know what FRBs are. We have lots of clues. But even if we never figure out what they are, they're tremendous probes of the matter distribution in the universe, the locations of these missing baryons. They should be, I say, intergalactic medium, but there's a whole web, and exactly the nature of this web and the degree of densities and the size scales of all of this depends sensitively on your model and how for galaxy evolution and the growth of structure in the universe. And in particular, so for example, we believe that the halos of the galaxies in different simulations have different size halos and different density distributions in their halos. And so, what fraction of the missing baryons are in galaxy halos versus in the intergalactic medium proper. So as along the line of sight to any FRB, there's also this circumgalactic medium contribution that FRBs now give us a probe of. We can now statistically, with enough of these sources, you need to really have lots of them all over the sky, we can statistically start to probe the matter content in circumgalactic media of galaxies in ways that we haven't been able to before. So we can do things also. We can constrain with FRBs the size and matter content of the Milky Way halo. This is a plot from a project by PhD student Amanda Cook, where we can, these are galactic radio pulsars down here. This is a sign of the latitude of the galactic latitude. That is, in galactic coordinates, galactic latitude 0 is in the plane, and 90 degrees it would be totally out of the plane. This is galactic latitude, and this is dispersion measure. Here are all radio pulsars. You see there's this, and these are all the FRBs. You see this interesting gap that's teaching you about where the Milky Way halo starts to ends. And we're going to try and fill that out and learn about the halo that way. Here's a more modern or more recent version in Science magazine from Ryder et al. Of the Marquardt relation. Again, extragalactic dispersion measure versus redshift. And you see now ASCAP has a few more sources. In fact, this is the highlight of their paper, one at redshift 1. So very, very, very distant indeed. The color scale doesn't matter so much, but this has to do with their selection biases for where they can and can't find FRBs. You see that it's harder for them to find more distant FRBs. That's just the detection probability is very easy for them to detect them here, where they have all the sources, and harder for them to detect here. But in any case, the main point is that there's, with a few sources that you can start to map out the DM redshift distribution, but you can't yet start to really determine the density distributions in circumgalactic media and things like that. But it's not just the dispersion measures. So I've talked about the dispersion measures. There's a lot more to it than that. The radio waves, so gamma ray bursts are great. Don't get me wrong. I know I'm here at Stanford. I don't mean to say anything. I love gamma ray bursts. They're awesome. But there's lots of energy. But radio bursts get encoded with the interaction of the radio waves with the matter, not only through dispersion, but also through, for example, so you get the plasma column depth, but you also get the plasma distribution, first of all, because of this phenomenon called scattering, where you can see here, this is a dispersed fast radio burst. This is what the fast radio burst profile looks at high frequency. And here you see at low frequency, there's a much longer tail. And that's multipath scattering due to inhomogeneities in the distribution of the free electrons. So if the free electrons are perfectly uniform along the line of sight, you don't see any of this scattering. But if the free electrons are clumpy, then radio waves that would have gone away from you get scattered back into the line of sight in a frequency-dependent way. And so this amount of scattering we now have for every FRB, we can either measure scattering or we can constrain it. And so that's another probe of the matter through which it's traveled. Also, we have scintillation. That is, we see structure in the spectra that is due to twinkling, just like twinkling of the stars, that has to do with the motions of the inhomogeneities in the density and homogeneities of the plasma. We can even get at magnetic fields, and that's what this plot is down here. This is it's kind of small. I'm so tempted to escape and make it bigger. It looked good to me before, but I won't do that. But anyway, the main point is that we measure Faraday rotation. Many of these fast radio bursts are hugely polarized. Sometimes 100% linearly polarized, sometimes 0, sometimes circularly polarized, but often they're highly polarized. And if you have a linearly polarized signal traveling through a magnetoionic material, you have Faraday rotations, a different index of refraction between circular and the two signs of circular polarization that translates basically to a frequency-dependent rotation of the linear polarization angle. And that's what's being shown here as a function of radio frequency. You can see the oscillations in the linear polarization angle, and we can measure the rotation measure, the integrated electron density, the combination of the integrated electron density and line of sight magnetic field. So we can measure all of these things with FRBs as well. So you get information about the magnetic field in the intergalactic medium, in circumgalactic mediums, in other galaxies as well. So this is a new probe of the very distant universe. So dispersion, multipath scattering, scintillation, rotation measures, we can do all of these things. But you need a lot of them. You can't, so there's lots of promise here. To understand them, you need more. And to make use of them as probes of the distant, of the universe, you need more of them. Now, let's say you could do a survey and find tons of these things. In time domain, time domain survey discovery kind of has two types of discoveries that give you progress. You can either find what I call the jewels. You find 1,000 sources and they're all kind of boring, but one of them is really incredible and teaches you a huge amount. So like a Rosetta Stone, but you do need to find a lot to be able to find those jewels. And then there's the sort of population studies, the big statistic where you can look for trends, look for correlations. You need large numbers, and in that case, you really need to understand instrumental biases, because you don't want to, if you're not detecting some corner of parameter space, then you're going to miss a correlation, or you'll see a fake correlation. So you have to understand your instrument exposure sensitivity. You're all familiar with these things. And no matter what, for either mode, you need a lot of sources. And so that brings me to the CHIME telescope in Canada. This is it's called CHIME. This is the Canadian Hydrogen Intensity Mapping Experiment. And this might not look like a radio telescope to you, but I assure you it is. This is in Penticton, British Columbia, in the Okanagan Valley, if any of you is familiar with that. And these, the reflectors here, not like the Parkes telescope, which is a parabolic reflector. These are cylinders. This is a large structure, so this is 100 meters in length, 100 meters, and each cylinder is 20 meters across. 20 meters, so it's 80 meters by 100 meters. Total collecting area, you could do the math, but it's like, I made the joke last night, but I'm going to do it again. 5 hockey arenas, just to give you a sense for those of you who weren't there. And what you see is along the, and by the way, the cylinders are oriented exactly north-south. And so, and there's no moving parts. It's a transit telescope. That is, it just stares at whatever's overhead. And so you don't have a choice, so you can't point it. Well, you can point it a little bit digitally. This is a digital radio telescope, entirely digital. But the sky rotates from east to west every day, and we can survey the entire sky, the entire northern sky, north. We can actually see a little bit south, but north, the entire northern sky every single day. This is not a conventional radio telescope. It's very different. The antenna, so basically these cylinders focus onto antennas. There's 256 antennas hanging along the axis of each of the cylinders. So it's a total of 1,024 antennas. Each is dual polarization. It's 2,048 signals going into a massive correlator, massive on-site correlator that is located in part in a little hut that you can't quite see under the cylinder. There's 2 huts, and then also in these shipping containers. And these are, there's massive computation going on all-site, as I'll tell you. This is the CHIME fast radio burst team standing next to the instrument and some of our funding agencies. Here is the signal path schematic for the system. Now, I should have said CHIME. Yeah, I should have said this. The name comes from Canadian Hydrogen Intensity Mapping Experiment, which is a cosmology experiment of which I am not part. The idea was to map neutral hydrogen at high redshift in the redshift range 0.8 to 2.5, which dictates the frequencies to which this telescope is sensitive, 400 to 800 megahertz. So it's redshifted neutral hydrogen, and the idea is to map. And it's doing that experiment. I don't work on that. But it can search for fast radio bursts at the same time. So this telescope does everything at the same time. It's a phenomenal design. It has, you see, from the 4 cylinders, we collect 512 dual polarization inputs. That's a total of input data rate of 13 terabits per second. So 13 terabits per second going into the world's largest correlator that's located on site. It's an FX-style correlator, for those of you familiar with these types of things, based on field programmable gate arrays built by my colleague Matt Dobbs at McGill University Cosmology Group. That's what's in those little huts that are underneath the reflector. And then a GPU-based X engine that, so the F engine splits the radio frequencies into frequency channels and then and digitizes. The X engine then digitally forms beams on the sky. So combines all of the signals for any radio frequency into digital beams on the sky by adding in appropriate delays from for all the antennas in real time. And those signals can go out to 3 experiments. One is the cosmology, the 21 centimeter mapping experiment. Another one is a pulsar observing experiment. And the one I'm talking about is the CHIME fast radio burst experiment, which consists of these stationary digital beams on the sky, as I'll explain, and 1 millisecond sampling of each beam with 16,000 radio frequency channels. So as I said, the F engine is under the dish, under the reflector, and the X engine is in the shipping containers, and the FRB back end, which is also huge amount of computers, is on the site. Everything's on site. Our power bills are high. So the way this works is if you have one antenna on a cylinder, you see a huge swath on the sky, in this case oriented north-south. And that gives us, we call it the primary beam of the cylinder, and that gives us the huge field of view. So from horizon to horizon. And now if you put many antennas on a cylinder, you can think of it kind of like a diffraction grating. We do FFT of this, and we can form these digital beams they're essentially pointing at different places within that primary beam and along the north-south direction. And then if you populate all 4 of the antennas, all 4 of the reflectors with these antennas, then you also get east-west direction. East-west direction. So effectively, and this is what it really looks like, there's 1,024 digital beams that has 120 degrees north-south and depending on radio frequency, about 2 degrees east-west. So we're talking a field of view of over 200 square degrees, which is very, very unusual for a radio telescope. Radio telescopes typically have much smaller. And not only that, the field of view is enormous, but because we have all these digital beams, effectively it's like having 1,000 Parkes radio telescopes all operating simultaneously, each one looking at an independent position on the sky. So you're looking, it's like, and actually it's for those of you in radio astronomy, it's not just like the Parkes telescope, like the Green Bank telescope, the largest fully steerable radio telescope in Green Bank, West Virginia, is a 100-meter aperture. That's about our sensitivity. It's like having 1,000 Green Bank telescopes all operating simultaneously and each sampled every millisecond across the full radio frequency band, digitized to 16,000 frequency channels. Now that's a huge amount of data. That's a huge data rate. And so going into the FRB search engine, that's 142 gigabits a second, and we can't possibly save all that data. So this experiment is a trigger experiment. We have, we're constantly searching in real time for these FRBs, and we buffer data. We buffer, we search total intensity data, so we combine the polarizations and we search that total intensity data that's at a cadence of 1 millisecond. That's, so here we form the digital beams. We send it to another set of computers, the FRB search engine, that first of all has to do real-time removal of radio frequency interference. This is a nightmare in radio astronomy. There's cell phones, there's airports with the radar, we see all sorts of stuff. We have to do we have to de-disperse. We don't know in advance what the dispersion measure of any FRB is going to be, so you have to do thousands and thousands of trial dispersion measures. And then we also, it's lots of stages of RFI, radio frequency interference rejection. But in all of this, we buffer data. We're buffering, and when we see the trigger, we quickly dump the buffer and save it. And if it's bright enough, we can not only save that in total intensity data, which is kind of small, but we can also save, if we choose to, we can save the raw voltage data from all of the antennas. So preserving the full polarization information at a much, much higher cadence than we search at. So there's 2 sets of data, one where we can just see what the detection operates on this 1 millisecond cadence, full intensity data, and we also have a buffer of the full raw voltage data that will allow us to better pinpoint on the sky and determine polarization information and all of this. So that, and then we have all sorts of other logic following it to, for example, filter out the annoying galactic foreground sources. So we see the crab pulsar all the time, and all these radio pulsars that I used to spin, I know Roger, other people, we love them, they're wonderful, but it's a huge noise source for us, and we have to filter them out. Unless they're really interesting, then sometimes we'll save them. And then everything in massive databases storing all of this information. And since it's a trigger experiment, if we miss it, it's gone. If we don't catch it in real time, then we've lost it, which means that we have to be very careful about our instrumental biases, because what are we missing, what are we not missing? We also have a system that injects fake FRBs into the real-time data. In principle, it's not operating at the moment, but we're working on it. That then tells us our instrumental biases so that we can do population studies. When we first started, we didn't know if we would detect these in our band. We weren't sure, but we started detecting FRBs down to 400 megahertz, the lowest frequency at the time that was ever seen. You can see our first few detections there. Now I've started to plot them where they're all pre-de-dispersed. So they all have different dispersion measures, but we tend to plot them all de-dispersed. And I showed this last night. So This is the number of FRBs that had been detected before CHIME turned on by the different telescopes. And you can see there the Parkes telescope was the first, and then there's several others that were finding some. There's a couple of Arecibo ones that you saw. I showed you the first repeater, the ASCAP ones. But then when CHIME turned on, it became a whole other story, because CHIME has this tremendous field of view, and we just clean up on this transient source. So astrophysics in the CHIME domain is a little bit different. It's unrelenting. We have FRBs flowing in constantly, and it's an interesting challenge to maintain those the data rates and handle it all. So now I thought I'll just mention some of the jewels that we found in the data. I talked about this one last night because it was really quite gratifying. As I said, one of the models for FRBs is that they're magnetars, these exploding neutron stars. And to our shock, we detected one magnetar, a galactic magnetar, which is not known to produce radio bursts. In 2020, just after the COVID lockdown, this is one of the brightest bursts we have ever, the brightest burst we've ever detected. It's not so obvious because it wasn't overhead. It was in the far side lobe of the telescope. So, this is diffraction limited, well, it's not a Bessel function or whatever, the aperture, the diffraction pattern of the primary beam. You have side lobes that extend very far over. This was way far side lobe. So this is where we're down in sensitivity by a factor of 10,000 or something. This is an enormous burst, and it occurred in the direction of a galactic magnetar that at the time was exhibiting intense X-ray bursts. So it was pretty amazing that we found this, and then I just very quickly explained why we don't think they're all magnetars, or at least that event proves that some FRBs are magnetars, but not all necessarily. This is a plot with distance on the x-axis in parsecs. So this is inside the galaxy, and this is cosmological distances. And this is the observed fluence, how bright the source appears at Earth. And you see, here are galactic radio pulsars. They're nearby at low distances. Here are the fast radio burst cosmological distances. They're about the same brightness at Earth as are these. No surprise there because, we use the same telescopes to observe them. And here is that galactic magnetar that went off in 2020 that we detected. The Caltech group using STARE-2 also detected it. And you see way brighter than anything we've seen from the galaxy before. And these these diagonal lines are lines of constant energy. So here, and these are by 3 orders of magnitude. So down here, you're at 10 to the 29 ergs. Here, you're up at 10 to the 44 ergs. And you see that the energy of the galactic magnetar is similar to the energies of the least energetic FRBs. So the least energetic FRBs, well, those are consistent with being magnetars. But you see, there's 6 to 9 orders of magnitude in energy still missing. Still quite an energy gap to go to have magnetars be all of FRBs. And so I'm not convinced that all or even most FRBs are magnetars. Well, here's another curious one. This is another jewel in our population of FRBs that we found. This is one this is a lot of work done by postdoc Daniele Micheli, where you see in one few second envelope, so you see now this is like a total over 2 second long pulse. You see individual bursts, and you can see them here in frequency space. These are equispaced. So these, we fit a beautiful, very simple model, and each pulse comes at exactly an integer multiple of 216 milliseconds. This is very significant. We estimate the significance of this periodicity at something around 6 to 7 sigma, depending exactly how you measure it. You have a periodicity every 216 milliseconds. That is something that smells like a neutron star, we've seen, that is the classic period for a radio pulsar. But this one is not, is cosmological distance. How could a radio, a neutron star rotating, that's comparatively slow for some radio pulsars. Why is the luminosity so high? I don't know, but something has to be periodic. Now, this is the only one where we have a significant periodicity. Out of thousands of bursts, we haven't seen another. We've seen some that look a little periodic, but they're not statistically significant. So, it's interesting. Now, in terms of population studies, so I've given you a few, this other jewels, I talked about one at lunch, one that's periodic, it's 16-day period, but I won't talk about it here, there's not enough time. Catalog type of population, how am I doing time-wise? How long? 5 minutes? I have 5 minutes? Okay. Yeah, well then I want to get to something, but it's the population style we can do. Our first catalog we published had 500 FRBs in it, and we can measure the power law index of the cumulative fluence or flux distribution. Because for a simple non-evolving population in Euclidean space, you expect an index for the cumulative fluence distribution about minus 1.5. 3 halves is the classic value, and that's what we measure. And you might say, well, it's not, if you're in a cosmological distances, it's not Euclidean, but the CHIME mean redshift from the dispersion measure distribution is around 0.5. So it's not yet inconsistent, but we expect in our second catalog, which we're working on right now with 4,000 events, that we should start to see cosmology from the fluence distribution. We also know from our injections that we are hugely we're missing huge, large fraction of of scattered FRBs. So there's a large population that CHIME can't see of scattered FRBs that should be detectable at higher frequencies. So the rate we have a lower limit on the rate. And let me just highlight also that could there be multiple classes of FRBs? So for sure you say repeaters and non-repeaters. It sounds like 2 classes. But what if non-repeaters are just going to be repeaters, you just haven't waited long enough? So, but one thing that having a large number of statistics, large number of FRBs, you can compare, this is now width and a measure of the spectrum. This is how broad the spectrum is, where around 0 is where it's very broad band, covers the full CHIME band. And you see the repeaters are in orange and the non-repeaters are in green. And you see the non-repeaters tend to have very broad spectra, that's the spectral running of 0, the very broad spectra, and much narrower widths. Here, the typical width is just under 2 milliseconds, whereas the repeaters have much broader widths. That's the orange one, much broader widths, and tend to be narrower in radio frequency, narrower bandwidths. So it's hugely statistically significant. Does that mean that repeaters and non-repeaters have different engines, central engines? Is it different physics? We don't know. We don't know. There's certainly overlap. Very new result that we just have is now we have about 50 repeaters, and we can compare the distributions of dispersion measures of the repeaters and non-repeaters. Again, you might think the distribution, the typical dispersion measure for a non-repeater, if it's a different source class and has a different environment, let's say one is in supernova remnants and spiral galaxies and one is on the outskirts of a galaxy, it's an old object, you might think that the host contribution should differ. And so you might expect the dispersion measure distributions of repeaters and non-repeaters to differ. And in fact, we measure that. Now, for the first time, we've seen a different distribution. The DM difference, the repeaters have a lower mean DM than non-repeaters. And you can see here the differences. It's at about a 3 sigma level. You can see the different distributions. The orange is repeaters. These are cumulative distributions. So you might say, so the environments are different? But actually, no. We think this is an expected observational bias because in order to detect a repeater, you need at least 2 bursts. And if there's more faint bursts than there are bright bursts, then you should see the nearby repeaters. The repeaters should be a closer population because you're more likely to detect them. And so we're not sure that this is a signal that they have different environments. It could just be observational bias. You're going to detect the repeaters first. The closer repeaters first. So even if they're distributed identically in redshift space and have identical environments, you would still expect to see repeaters have slightly lower DMs. So we're not sure what it is. We need a population study, and that's what we're working on. Okay, and just the last point is, so much of what I've described, the answers to so many of these questions, both what are they, where are they, what kind of galaxies are they in, where in the galaxies are there, all of the uses of them as probes to understand matter distribution, intergalactic magnetic fields, circumgalactic media, all of this would be so greatly aided if we knew what galaxies and what redshifts all of the CHIME FRBs are. We don't. CHIME has poor angular resolution also. About 1 arc minute in the best cases. Sometimes we can do better. For bright ones, we can get down to 10 arc seconds, but it's still not good enough. So it's not great for realizing their potential as probes. So that's CHIME's Achilles heel. But we have a plan. So thanks to the Gordon and Betty Moore Foundation, we are building Outrigger telescopes. And we are developing, it's to do very long baseline interferometry. CHIME is located here in British Columbia, and we're building 3 CHIME-like telescopes, smaller versions of CHIME, to do very long baseline interferometry on every CHIME FRB. The idea is to get at least 1,000 FRBs precisely sky localized, and our goal with these very long distances, this long separation of these interferometric arms, long baselines, we think we can get to 50 milliarc seconds. That is not only determine for every FRB what galaxy it is in, and hence the redshift and the distance, but where in the galaxy. Is it in the spiral arm? Is it on the outskirts? Is it in a star formation region? That's what our goal is. And I said first light expected 2023, and indeed, as I'll describe, so here's what we're trying to do. Now you might wonder how you can do, so if you know about VLBI, you know it's all, to get those kind of precisions, you need to calibrate very carefully your baselines. And that's very hard to do when you don't know where the source is going to be and when it's going to happen, and if there's a calibration source nearby. So if you know about VLBI, it seems impossible. Our plan is to use radio pulsars, in fact, as our calibrators. There's enough radio pulsars in the huge CHIME primary beam that there's always one that we can see. And so we're going to watch them and throw them away if no FRB happens, and if an FRB happens, we save it as a calibrator. And we've already pioneered this. We've already done some experiments at using some Pathfinder telescopes in Greenbank, West Virginia, and in the Algonquin Park in Ontario. And we have localized 1 FRB in this way using CHIME to the outskirts of the spiral galaxy. And that's a paper we've just submitted. And so here is the first Outrigger. It's built. It's located in Allenby, British Columbia. You see it's a smaller version of CHIME. This is a little trolley that grad students get to ride on to fix or hang antennas. You can ride along in that trolley, lots of fun. He's a bunch of grad students who just finished wiring up this Outrigger in Greenbank, West Virginia, and you see it's ruled. They all have to look at the same sky that CHIME looks like. So CHIME looks overhead, and Greenbank and then therefore has to tilt. And the idea is they buffer data until CHIME has a detection, and then it sends out over the internet a signal, dump your buffer, and then we bring all the data together to correlate it in a central location. And here is just after the analog deployment. You see all the cables went in, lots and lots of cables here, and it all went into the shipping container at Greenbank where the electronics are located. And these are some very happy grad students because they started getting some real data on the sky. And the third one is in Hat Creek, California, where I'm flying tomorrow to check out how the foundation holes are being drilled This is the largest drill bit I'd ever seen. And you see, this is the field where the CHIME telescope, the CHIME Outrigger is going to be located sometime by the end of the summer. It will be built, I hope. And here's me standing on a large chunk of bedrock that they just pulled out from this. And you know, I used to be an astrophysicist, and now suddenly I'm learning about concrete and drill bits and construction permits and all sorts of fun things like that. But it's coming along, and we're very excited. And in summary, you know, FRBs are still pretty mysterious. There's lots of evidence, I think, but this is, I can't prove it, but there's lots of evidence there's multiple classes, different morphologies, some repeat, some don't. Well, we don't know. But no matter what, even if we never figure out what they are, they're great tools for studying the universe's matter distribution. Although I think to make that happen, you really need to have redshifts for these objects. And the upcoming Outrigger telescopes, we're making a lot of progress. We're building them up, and we hope that soon we'll have redshifts for all our FRBs. And by the way, if you want to detect FRBs, you want to study them, you can sign up for alerts. You can get on your cell phone every time we detect an FRB if you want. And in summary, science happens in complicated ways, lots of twists and turns, and a telescope designed for hydrogen mapping scores big in the time domain. That's CHIME. Not totally unexpected, but very exciting. And so thank you very much for your attention.
We've got time for a few questions. Maybe I can take the privilege of asking the first one. You often quote this number of 1,000 per day. And what I'm curious is that a sensitivity limit, or is there any sign of intrinsic cutoff in the distribution?
Totally sensitivity limited.
So if you could go fainter, could it be hundreds of thousands per day?
Yes.
Interesting. At some point, you're going to run out of stuff out there.
Yeah. So we're building a cord. So after CHIME, we're going to be building the cord telescope, and that should have a detection rate something like 10 times CHIME. But the square kilometer array, you might have heard of that radio telescope, should also have you could do. You know, the next generation of radio cells, as students here, if you're interested, you could be detecting hundreds of thousands. Tomography of the whole universe.
Sounds good. All right, questions? You can call them.
Vicky, let me talk. What ideas are out there to look for fast non-radio bursts, in particular, so analog things in the odd parts of the electromagnetic spectrum or beyond?
Counterparts to fast radio bursts in particular?
Well, yeah, there would be eventually, but I mean just actually observationally trying to find something like a fast radio burst, but in radio or in optical or infrared or X-rays and so on.
Well, I mean, I think Fermi does a great job in gamma rays, if that's what you mean, and also in hard X-rays. I think it goes down to 8 keV, so X-rays and gamma rays, that's been done for years, and we know lots of things that burst, like magnetars and gamma ray bursts. In optical, there are some experiments that can go, the optical transient detectors, like the Zwicky transient facility, or some of these, they don't have the millisecond kind of cadences that you would like for very fast optical transients. Yes, yeah, the technology isn't quite there, yeah, those are the ones I'm familiar with. I don't know, is there some region of the spectrum you're particularly interested in? Yeah. It's technology limited.
Okay, yeah, thanks. This is a technical question. Is there a simple way to understand why a GPU is good to build a correlator?
Why what?
Sorry?
What did you say? Can you say it again?
Why GPUs are good for building correlators?
Why GPUs are good for correlators?
You could probably do it in other ways too. It was cheap, fast, commercially available, off the shelf.
It's a particularly appropriate architecture. I just don't see.
No, I mean, you're doing FFT after FFT. It's something that's very, I mean, you could do it in other ways too. It was the cheapest option. And the truth is that we just got money to upgrade the correlator, and you can do the same kind of processing nowadays. We had 256 GPUs. I think we can do it in 20. Something much smaller that will take way less electricity these days. So I don't think it has to be a GPU, but that was just the most cost-effective option. And I should have said the GPU portion of the correlator is built by Keith Vanderlyn at University of Toronto.
One of your slides you had nanobursts at nanoseconds. Is that also at radio frequencies?
Yes, yeah, so the Crab pulsar has nanoshots, very short bursts. I haven't studied those, but
About this big.
That's like a
Speed of light.
cycle of radio waves.
that's true. Yeah, very, very short, yeah. That's, neutron stars are pretty amazing objects. Yeah, we don't have the capability to detect that with FRBs, but we could, in principle. You need, yeah.
Generally speaking, what's the relative contribution of the dispersion measure of the host galaxies to the overall dispersion measure?
So it shrinks as you go further out because the IgM contribution just grows. So if you look at, for example, the first repeater that was in that dwarf galaxy, it's about 50-50 as we had actually just guessed to begin with. It was about that. But if you go to a very distant galaxy, it's very quickly it starts to be totally dominated by the IgM.
Well, we've got a reception afterwards, and some hungry graduate students are headed that way, so let's thank Vicki again. And,